Hey y'all, welcome back to Stat and Research 2. We are starting our third week where we will be talking about randomized complete block designs. But before I start talking about how many videos we have and what's expected of you this week, quick class announcements. First, I'll be posting homework 1 solutions, or they should be posted by now. Thank y'all for your patience. We had some last minute add-ins to the class. I didn't want to punish them for adding our awesome class late. And so that's why these are getting posted a little bit later than I would have expected. Homework 2 solutions will be posted Tuesday morning for other reasons. And then after that, I'm going to try and post homework solutions on Monday. Here's the thing. If you turn in the homework after the solutions are posted, I'm going to have to give you a 0. This is your warning. So try to get your homeworks in by the deadline so you don't have that issue. I think that's all the class announcements I have right now. So let's get started on talking about this week's lectures and what's expected of you this week. This week we have 3 lectures. The first one, which is going to follow right after this, is going to be introducing blocks, defining it, and trying to give you guys a reasoning on why we should block. The second one is going to be really talking about the statistical model, the ANOVA, underlying a randomized complete block design. The third video is going to be focused on testing blocks. Foreshadow, you don't want to test for your blocks. That will make more sense, but just get in your head that we aren't going to actually test for blocks. Oh, your assignment for this week, I almost forgot, is homework 3, and it is due Saturday by midnight. And that's all the class announcements for today and what's expected of you for week 3. So let's get started on lesson 3A, where we're talking about blocks. So in this lesson, again, we'll be covering the definition of blocking in terms of an insecticide example, which we'll carry out through this entire lesson, and kind of how to perform randomization for a block design. This week, again, our new design is called a Randomized Complete Block Design, or RCBD. Okay? Now, the idea of blocking is to be efficient with our resources and help explain unexplained variability. So how do we remove part of the unexplained variability and change it to systematic variability? Well, in lesson 1, we kind of talked briefly about this, where we were introducing experimental designs in terms of blocks. More specifically, it was like the shrimp example with our assistants in lesson 1. But in this lecture, we're going to talk a little bit more. Another idea that we could use is covariates, which is for continuous predictors, which we'll talk more about later. So we'll talk more about this later. This class is focused right now on block. So with a block is a set of EUs that share a common characteristic into which we make a separate random assignment. Now, this random assignment is important because it can help us understand we have a block in our experiment. This will hopefully make more sense as we travel through our notes this week. Now, when we are choosing blocks, it's not just out of the blue random. Typically, you want to really talk to an expert in that field and make sure you are understanding the different sources of variation that can impact our experimental units. Some common blocking factors, but of course not all of them, are your age or weight of an animal, different batches in a manufacturing material, time and day, physical separation of plots. This is going to come back in our example that we're going to be talking about today, or maybe the gender of humans in a medical study. Okay. The example that's going to carry us through this lesson / week is going to be our insecticide example. So we have a researcher who's conducting an experiment to compare the effects of 3 different insecticides on a variety of string beans. To attain sufficient amount of data, it was necessary to use 4 different plots of land. Each plot was subdivided into 3 rows. Each row was planted with 100 seeds and then maintained under the insecticide assigned to the row. So, what's our interest? Our interest is the seedling survival rate when applying different insecticides. We have 3 treatments, which just we'll label them as A, B, and C. Then we have rows of 100 seedlings, which is our experimental unit. It's our experimental unit because the row is what we're applying our treatments to, and our response is the number of seedlings that arrive. So we're going to have 4 plots, and in each plot we're going to have 3 rows. To help give us a better idea, here's a little cartoon. So we have our plot 1, 2, 3, 4. And notice there's a lot of variability across these plots. And even if we weren't in an experimental design class, we'd hopefully use kind of our scientist intuition. And we'd probably think that if we have 3 treatments, we would randomly apply the 3 treatments across the rows in the plot. And so what I mean is, here's row 1, 2, 3. Maybe we randomly go A, C, B. So without even a design of experiment class, we would probably have this thought process because we're smart cookies. And then maybe we would randomize this to be B, C, A. Okay. Notice that when we did this kind of random assignment, we could do it for all of them if we want. Just kind of making these up in my head as I go. That a complete set of treatments is in each block. So we have A, B, C, A, B, C, A, B, C in each block. So what's happening here is that each plot of land is going to act as our block, as our block. So these EUs, the rows, we would call homogeneous to each other. So within plot 1, we would expect these 3 rows to be as homogeneous as possible. Same thing with plot 4, we'd expect these 3 rows to be homogeneous within this plot. Okay. But notice that there's a lot of plot to plot variability. So here we have a lot of shade probably from our nice trees. Over here we have a farm and a goat. I don't know what the goat's going to do, but the goat might affect plot 1. And from plot 2 to 3, we have a lot of drainage coming in. And so from plot to plot, there's a lot of variability, which is okay. And it's actually beneficial that we have a lot of plot to plot variability. It's actually a good indicator that we are using a good blocking variable. So let me repeat that one more time. Within block, we want homogeneousness. We want these rows to be as similar or as same as possible. Okay, but from plot to plot, it's okay for them to be heterogeneous and different. And we'd expect them to be different in this case because of where they are in our made up fields and line. So it's important when you think about different variables to block, we want the blocks to see some difference. It's helpful to have block to block variation. But within our blocks, we want them to be as similar or same as possible. Okay? So again, block is just a way that we can manage extra systematic variability besides just our treatment. Because again, our end goal is to see if the treatments have an effect. And by implementing blocking, we're trying to reduce the unexplained variability. So in our insecticide example, we had the fertilizer, the drainage, the wind shelter, all these other factors that we were able to hopefully block by the plots. And typically our blocks are scientifically uninteresting. They're not really important to us, but they're necessary to identify and to manage so that we can hopefully be able to relate those environmental factors to variability and not just leave it in the unexplained variability. Now, we talked about blocking, but the question is, how can we also identify it? So one way to identify blocking is that we identify a partition of the EUs into blocks such that the EUs, or the experimental units, within each block are homogeneous. Yes. And the EUs across the blocks are possibly heterogeneous. Okay. Again, within block, we want them as same as possible. Across block, we want them to be different. That's kind of why we're blocking. And again, in our insecticide example, our EUs, the rows within the within the plots are homogeneous, and the EUs across are heterogeneous. So with randomization, within block, we say that the randomization is done within each block. So this table we have here of the insecticide data kind of shows us how we want to randomize. So with 4 plots, which again are our blocks, we have done 4 randomizations. And so in plot 1, here's our randomization. We just did 1, 2, 3 for our insecticide, and then that's our response. Again, randomized the rows, randomized and randomized. So these are the insecticides that are going to be applied to row 1, 2, 3, row 1, 2, 3. And again, this is a randomized complete block design. It's complete because we see every treatment in every block. So it's complete because every treatment in every block. Okay. Now, if we ignore randomization in blocking, we are going to get something that could potentially cause confounding between the treatment and the block effect. What I mean by that is, let's say we have 3 treatments and we have 3 blocks, and we have 1 experimental unit per treatment block. This is important. In a randomized complete block design, we only have 1 EU per treatment block combo. Then we could possibly get a randomization that might look like this. So we have block 1, 2, 3. Then we have our EU 1, 2, 3. And let's say treatment 1, treatment B, and treatment C. We could get something that looks like this if we don't randomize the treatments within the block. So again, here's block 1. Okay. So our question now, if we had this type of setup, is it the difference in treatment, or is it the difference in block that is impacting our results? But if we go back to this type of design, we're not going to have that type of question. Okay. So here, this almost non-randomization within block is almost making us question, is it the treatment A, or is it the block that's really causing the difference? Okay. So quick summary is, with the randomized complete block design, we will see a difference in randomization within each block, and the blocks are picked so that the experimental units within the blocks are homogeneous, and the EUs, or experimental units between the blocks, can differ. So again, in this video, we're just trying to introduce the idea of blocking, how to identify it. In our next video, we're going to talk about the statistical model and do the ANOVA behind it. See you guys in the next video. Hope you have a great day.